For many centuries, humans thought of the universe as a straightforward place, assuming that our planet, Earth, was the center of all existence. The sun, stars, and other celestial bodies were believed to circle around our home in perfect harmony. This perception of the cosmos stemmed from our natural tendency to place ourselves at the center of everything. However, as the human understanding of the universe evolved, we embarked on a journey that would eventually lead us to discover our true place within a sprawling galaxy known as the Milky Way. This journey of cosmic discovery is a fascinating tale of determination, innovative thinking, and scientific breakthroughs. To accurately identify our location within the Milky Way, it's imperative that we first understand the true structure of our galaxy. The night sky offers the first set of indicators, presenting us with a faint, luminescent band of stars, a celestial ribbon that we recognize as our galaxy. This band-like formation suggests that we inhabit a flattened disk rather than a spherical structure. If our galaxy were spherical, we would witness a significantly higher distribution of stars scattered evenly across the entire sky. Moreover, the band appears to bisect the night sky, implying that we exist within its plane, neither situated above nor beneath it. It remains impractical for us to vacate this plane to gain a full perspective of the Milky Way's shape. Such a journey would require traversing hundreds or possibly thousands of light-years perpendicular to this plane. For context, consider Voyager 1, the most distant human-made object. Despite its near half-century of space travel, it has only covered a distance equivalent to 0.02 light-years. This underlines the magnitude of the distance that we would need to travel to fully observe the structure of the Milky Way. However, the lack of technology for direct observations did not dissuade us from determining the shape of our galaxy and our place within it. The first notable stride in this journey was taken in the 18th century by William Herschel, who is best known for his discovery of the planet Uranus in 1781. Herschel was not just an astronomer, he was a mapmaker of the cosmos. His primary tool in his investigations was his handmade telescope, a device that allowed him to peer deeper into the cosmos than anyone before him. Herschel dared to take on a task that no one had ever attempted, to map the stars of the Milky Way. In the late 1700s, with the help of his sister Caroline, he embarked on a grand project. He divided the night sky into approximately 600 zones and, with relentless patience and precision, catalogued the position and brightness of each observable star within these areas. His process involved viewing the night sky through his telescope and marking the relative positions of the stars on a grid. His meticulous star count led him to propose that our galaxy was a disk-shaped structure. His observations also suggested that our solar system was close to the center of this structure. However, Herschel's map was not entirely accurate. He was unaware of the existence of interstellar dust, which blocks our view of stars in the Milky Way central region. As a result, Herschel's map showed the central region of the Milky Way to be much less dense than it actually is. Despite its inaccuracies, his map was a major breakthrough in our understanding of the Milky Way. It was the first map to show the Milky Way as a disk, and it provided important clues about the structure of our galaxy. To introduce the next important figure in our story, we jump ahead to the 20th century, where a curious astronomer at the Harvard College Observatory is making a discovery that would revolutionize the field of astronomy. Henrietta Swan Leavitt, an American astronomer, made significant contributions to our understanding of the cosmos, which in turn informed our knowledge of our place within the Milky Way. Leavitt's work focused on a unique type of star known as Cepheid variables. These stars pulsate, growing brighter and dimmer over regular periods. Leavitt's role at the Harvard College Observatory involved cataloging these stars, which led to her groundbreaking discovery. She cataloged 1,777 variable stars, and in 1908, she observed that there was a direct relationship between the luminosity of these stars and their pulsation periods. Brighter Cepheids pulsed more slowly than their fainter counterparts. This simple yet profound relationship, now known as Leavitt's law, allowed astronomers to determine the distance to Cepheids by measuring their pulsation period. Cepheids were established as the standard candles for measuring astronomical distances, enabling astronomers to measure distances up to 20 million light-years. Now, you might wonder how this helps us understand our position in the Milky Way. To answer this, we need to introduce Edwin Hubble. Before the 1920s, many scientists believed that our Milky Way galaxy was the only one in the universe. Even though astronomers had captured images of what we now know as neighboring galaxies, such as Andromeda, they were thought to be star systems within the Milky Way. The majority of astronomers assumed that the Milky Way was the entire universe. However, as telescopes advanced, some began to question this theory, noticing an increasing number of vague patches in the sky that didn't resemble typical star formation regions within our galaxy. A significant challenge at this time was the lack of precise methods for measuring the distances to stars, as stars vary greatly in size and brightness. One approach to estimating their distance was based on their apparent brightness, but a large, luminous star situated far away could seem as close as a smaller, dimmer star. This is where Leavitt's work became crucial. Leavitt had shown that Cepheid variables could be used to determine distances to galaxies up to 20 million light-years away. Inspired by this, Edwin Hubble set out to measure the distance to the Andromeda galaxy by studying a Cepheid variable star within it. His findings shocked the scientific community. Hubble discovered that Andromeda was approximately 930,000 light-years away, extending far beyond the confines of the Milky Way. Although this distance was about a third of the currently accepted value, Hubble's estimation was enough to confirm that Andromeda was outside the Milky Way, reshaping our understanding of the universe. The discovery that Andromeda is a flattened disk of stars, similar to the Milky Way, sparked a question among astronomers: where are we located within our own galaxy? This question was tackled by American astronomer Harlow Shapley. Initially, Shapley believed that everything visible to us was part of the Milky Way, a notion disproven by Hubble's research. Recognizing his error, Shapley amended his viewpoint and embarked on a diligent effort to catalogue galaxies, documenting as many as 1,249 in just 6 years. However, it was Shapley's work from 1914 to 1918 that played a crucial role in our quest to determine our position in the Milky Way. Armed with the powerful Mount Wilson Observatory 60-inch telescope, the most advanced instrument of his era, Shapley focused his research on globular clusters, densely packed groups of hundreds of thousands, or even millions, of stars that are gravitationally bound to form a spherical shape. These clusters are found above or below the plane of the galaxy and are among the oldest objects in the universe, some dating back over 10 billion years. Shapley discovered that these globular clusters were arranged in a spherical pattern around the galactic core, notably in the direction of the Sagittarius constellation. This was a significant observation because, if we were located near the Milky Way's core, we would see globular clusters scattered across the entire sky. However, most of them are only visible near the galactic center, indicating that we are positioned towards the outer arm of the galaxy. Shapley's calculations estimated our distance from the galactic center to be between 33,000 and 90,000 light-years, though modern astronomy has refined this figure to about 26,000 light-years. Today, the Gaia mission, launched by the European Space Agency in 2013, continues to refine our understanding of the Milky Way. Gaia's ambitious journey aims to create the most detailed 3D map of our galaxy ever conceived, surveying approximately 1 billion stars. This mission allows astronomers to study the Milky Way's structure, dynamics, and evolution, helping us better understand our place within it. With its precise data, Gaia is an astronomical game-changer, revolutionizing our understanding of the Milky Way and our position in the broader context of the universe. The discoveries made by Gaia continue to fuel astronomical research, propelling us further into the mysteries of the cosmos. Recently, astronomers discovered that a black hole suddenly flipped its direction and is now pointing at us, an exciting development in the ever-evolving field of astronomy.